Hello YouTube viewers, welcome to my show Computer Wednesday. In today's episode, we're going to talk about a very interesting topic of RISC-V or RISC-V. So let's dive right into it. Now first you have to understand every processor that you use, whether it be in your basically smart TV, whether it be in your smartphone, whether it be in your computer, has a core to it. The core is basically what we classify as instruction set architecture. Now you must understand all a computer core or a CPU is basically on and off switch. So how the heck an on off switch translates into an image? Now again, you can manually do that, and you must understand, like, okay, what if you have 10 lights and you're turning on and off at a pattern? But again, you are doing it, so how the heck a computer does that? So to do that, we create something what we call as architecture. Now this is on a hardware level. This is basically Intel's first quote unquote the foundation processor, basically 8086. This lays the foundation of modern computation. Now if you looked inside, something like this happens. Now if it looks like a blurry mess, it's supposed to, like, it would require you to have a good microscope to see what is happening here. Now this is the architecture. Now this architecture has a pattern to it, a reason to it. That region is logic. That logic is what we classify as instruction set. So basically they have a clock cycle. Basically they will do this many things in one period of time. That period of time would be inside a second based on the speed, basically 500 megahertz, 2 gigahertz, whatever have you. So they have a clock, they have this and that. Basically everything you talk about processor happens in this place. This is the architecture. This is the money maker. Now in this sort of architecture, they were in early computer days, like very early on, like computer are still like big machines that are consuming data tapes. Basically back in those days, there were two core architecture that people come up with. People came up with RISC architecture, very simple instruction set architecture. Now problem with that is that required a lot of RAM. Basically it needed something to feed the processor, because you have to understand, RAM was being made with what we call magnetic beads. Basically there were ferrite core and there were two cables going back and forth. So basically that's how they were addressing it. It was too slow. Basically if your processor were working at kilohertz, this was barely at, like, few hertz. So there was a very serious gap between RAM speed and processor speed. That created a problem that your processor was like idling most of the time. So people did not, that's like wasteful. And to get the most out of the processor, you had to have a lot of RAM at that time, because they were making like physically complex things. They were very idiotically expensive. So to solve this problem, some of it came up with a very smart idea. The people in Intel came up with this idea, CISC architecture. Now this architecture is basically, instead of waiting for RAM to provide information, it's like, okay, give us compressed information. Basically the complex, that's the whole point of CISC architecture. There's a complex instruction set. Is that instruction, even though it will barely have, like, let's say two things in it, basically two instruction, you can open that two instruction up into like 8 to 12 things. So your processor will do a lot of things. So this way RAM and basically CPU became independent of each other. You can have very little amount of core memory, and then you can like literally keep processing based on your CISC architecture. Side effect, it requires you to handle a very complex programming language, but it was friendly because it's like more or less how human talks. We don't talk about, like, you must have heard people classify computers as adding machine. We don't talk in that term. So CISC became very popular. It became a foundation. But as RAM prices started to come down, RAM actually became affordable. People are like, okay, CISC is not really that good because it's inherently complex. Like, complex is in its name. So that created a problem. It was very energy inefficient. Basically if you have 1 watt of instruction coming in and you want how much things you are getting done, it was very little. So they started to go back to RISC architecture and take something from RISC architecture. So they created SiFive. This is in your modern processors. Almost all modern processors are basically x86 processor are CISC hybrid. Basically they have a little bit of elements of RISC architecture and little bit of CISC architecture. But again, this is the sole reason why Intel failed to make a mobile processor, because inherently on a chip level, on a basically fundamental level, the system that Intel uses, or x86, is not efficient. It was built for a world that was like free on electricity. That time nobody was thinking about what about power consumption. Nobody was thinking about it. Like, you had like freaking power plants feeding into mainframe computers. So nobody was thinking about basically energy efficiency. However, when you're talking about portable devices, energy efficiency matters a lot. That's why Intel backed out. It's like, okay, we tried our architecture, it simply does not work. So this x86 became the de facto fault for everything, from server to main computers to almost everything. So this is the core fundamental of your computer. So what is the problem with it? If it has been working from 1980s, so what is the problem with it? Now, first problem is the early days people knew that this architecture is not efficient. So the way we compensated for that is we increase the speed. So early processor was like 500 megahertz, 600 megahertz. Then we started to increase the speed like from megahertz to gigahertz, 1 gigahertz, 1.2 gigahertz, 2 gigahertz, 4 gigahertz. So we started to do that. However, now we are reaching the end of what we classify as Moore's law. Basically, we are no longer in a position where our next generation processor would be like, okay, it would be half as the price and twice the performance. We no longer at that scale. Basically, the curve of Moore's law was like this. We reached this point. Basically, at this point in time, physics is stopping it. It's like physics is saying, hey, you already reached 7 nanometer. The early processors were like 200 nanometer, 500 nanometer. That's why I said you can use microscope to see that. But today's processor is reaching like, especially if you are talking about like 50 nanometers or 44 nanometer, you can't see that. You need electron microscope to see that. When you're talking about 7, you need a very good electron microscope to even try to see that. So once we started to reach that point, we can't go below this. Now you're like, it's 7. What if like we went 0.7? You can't do that simply because once we reach that level, physics starts to reach into what we call as quantum realm. Basically, it starts to behaving in odd ways. So basically, think of it this way: you have a transistor which is like, okay, on or off, and there is a gate that does that on and off. Basically, so gate system. Now electron can simply go YOLO. So if you make it too small, the electron simply says, I'm gonna go jump here. It does not matter whether the switch is on or switch is off. It simply goes through it. So that causes error, and this error is happening on a processor level. You can't write a software that can fix it because it's the software goes through a kernel goes through the instruction set. Instruction set is corrupted simply because your electrons are YOLOing around. So we cannot go make this much smaller. Now of course, during some polishing, some practice and some new design, some clever lithography, we can reduce it to 5 nanometer, but that's maximum. Like of course we can change to other materials, but silicon has reached that point. Silicon has reached the point where it's like, okay, maybe 5 nanometer, maybe 5 gigahertz. And you must have also seen, like we were going from basically megahertz to 100 megahertz to gigahertz. Why the hell we are not going from gigahertz to terahertz? We simply can't. That's the sole reason. That's why you are seeing a process that has been stagnating. Basically, we went from 2 gigahertz to 2.5 gigahertz to 3 gigahertz, and after 3 we started to like stagnate. It's like 3.5, 3.5, 6, 3.7, 4. That is happening because at this point in time we are no longer focusing on let's get as clock cycle as high as possible. We are not going there simply because we realized that it requires liquid nitrogen cooling to reach 8 gigahertz. Like old processors can also reach 8 gigahertz. Just no point in that. And on top of that, it becomes very inefficient, and at that high frequency the electron also starts to behave YOLOing around. It's like too many error happens. So people are like, okay, let's not focus on that. So modern technology shifted from making faster and better processor to basically, okay, let's put a lot of them. That's how the core war started. Basically we went from single core to dual core to core to duo to 4 core to 8 core. Right now you can buy 16 cores for a desktop system, and server directly went like 128 cores and all that, and your GPU it started to create small compute cores. There is like 2000 compute cores in your graphics card. So that's what happens. So Moore's law has already reached a maximum point. Basically, will we have improvement? Yes, but it will be very tiny improvement. It would be like from this generation to next generation, it will be like 15-20% improvement, and that's a lot. And most of the improvement will come from better design, better efficiency, better software support, not from the hardware. Hardware has reached its point. So that's the first thing. Like, so we can't push x86 anymore. Then the aspect of it that x86 has been like, it was the first architecture, you have to understand that, and people who created x86, first they did it in a hurry, second they did not have the hindsight, like they assumed that RAM would not be cheap. So based on their limitation, they created a badass thing. Like that's why we are still using it, but it had its limitation. Basically with modern knowledge we are like, yeah, this was very good at 80s 90s, but now it's like, yeah, now it's reaching a point where it's like we really can't push it. So the bloat happened is basically every few days they were adding new instruction to the main core instruction set. Now that core instruction set is right now is like 500 instructions. It's not supposed to be that many high. Like it's supposed to be like 50 to 200 or something like that. It should not be 500 to 3000. Some of the processors have like 3000. That's too inefficient. That's why mobile processors do not use x86. So, and if mobile is not using it, x86, so why not everybody is using ARM? Basically ARM became the de facto champions because once the memory became cheap and we have cache memory, basically memory on the processor itself, it became very cheap. So ARM came along, and right now at this point in time, if you collected how many computer cores have been sold, x86 is lower because ARM has taken over, because your mobile phone, smartphones are taking this, and Samsung also has to pay ARM corporation for that architecture. Apple has to do that. So even though Apple is making in-house processor, the architecture of the processor is from ARM technologies. So even though, like, let's say Hawaii is building their Kirin processor, Kirin 980, they still have to pay that. Snapdragon also has to pay that. So every Tom, Dick and Harry is paying ARM to the luxury of doing that course. Basically the architecture is still bought from ARM, so it is very expensive. You have to understand that x86 is not something that you want to build it, you can build it. Like Sony tried that with PS3. You can build it, and you can go to Intel and it's like, hey, I want license. But you must understand that requires a very serious amount of chunk to be taken out of your bank account. And even Samsung, Apple, they don't want it. Like even they have hard time. It's not like, okay, $1 per CPU. It's like, you know, few $billion for the IP, and then every like small percentage per processor. So this is a very expensive ordeal. And it's also copy protected. So even if, let's say Samsung had an issue, Samsung is like, hey, the security is having an issue. I write a security code, it's not working properly because I do not know what's happening in the processor, because it's a copyrighted thing. And even if they tried it, they can't directly implement it without get pissing off ARM system, and ARM can simply revoke the license and have lawsuit and all that. So there's a lot of problem in this. So we can't make our processor any faster. We are reaching the maximum limit. Too much bloat in x86 flat out, and the ARM is very proprietary and copyrighted and like $1 billion industry. So introducing RISC-V. RISC is basically the architecture that is being used for this, but RISC-V is a redesign of it. Basically, you have to understand this. When you go to a computer academy and all that, where you learn the actual how the heck a processor works, they can't show you x86. They can't they just because it's a proprietary information. So people generally create, like for computer books, you must have seen the price of computer books. They are high, like they are higher than medical books. And the reason for that is basically somebody has to actually design a processor there. Like, okay, this is how 16-bit processor works. This is how a 8-bit processor, or somebody has to sit down and design it. So designing that takes a lot of energy and effort. Now problem with that is like they try to make it as close as 86 but not too close, because then it's a proprietary violation. So in those sort of scenario, books have become very expensive. RISC comes along, it's like, hey, this is the architecture. I built the whole architecture. This was built in around 2010. The whole architecture is built, and they're like, okay, this is, make it for book, like whole architecture, take it and go. Now they took the architecture idea and they pushed it forward. They made it into an open source hardware. The benefit of that is nobody can claim it. Basically, you want to make a RISC processor, go ahead. Basically, if Samsung was making it, Samsung don't have to pay. Samsung started to make RISC, they simply don't have to say anything. They can ignore it, but the one thing they can't do is they can't say like, okay, Samsung made this. They have to say like, okay, we are utilizing RISC patents or a RISC architecture. They can simply make it. They don't have to pay. The money is the biggest selling point. So the instruction set architecture, it caught attention of a lot of people, like because you have to understand, right now x86 is dying, slowly it's dying, because even server is now starting being made of ARM systems, and soon ARM desktop should hit the market. Simple reason for that is ARM became so big that there are so many developers that can handle ARM architecture to the core level. Basically they can write the kernel itself. So people are now confident that they can write basically your 3ds Max, Maya, your Adobe Premiere and all that in a ARM architecture. Processing power is there, it's already there. It's just that code can also be basically converted now. So this many company came along. It's like 500 plus company came along, and of course there are multiple layers. So platinum members can help RISC along, and other members can utilize and have a talk. So there are big names in this. Basically big name Google is there. There is Qualcomm, because Qualcomm also does not like the idea of paying ARM. There is Samsung also does not like the idea of paying Qualcomm. Nvidia, because Nvidia is also like pushing it. Nvidia is playing a very long game, because if this works out, Nvidia can really push ahead their artificial intelligence department, not the GPU department, the AI department, which is the next big thing. So they are also supporting it. Basically, if you actually read this list, the list would be like who's who of the everything. Basically Western Digital is also there. There is basically Siemens is also there. Hitachi is also there. So many companies that, like, half of the companies I never heard, but most of them are enterprise grade equipment. So basically Ultra SoC, this company makes things for other companies to make. So you have to understand, like, so many company, it also includes Tesla. So let that sink in. So many company poured in their money, their support, infrastructure, and their IPs. So that's what's happening here. It's like basically right now, if you're like, hey, I want to use a Samsung memory chip, because Samsung is granddaddy of that. It's like you need to know how to communicate with that. There is a protocol for that. Samsung is giving that protocol to RISC for free. It's like take it and go. There are other companies, let's say Siemens, that is making their gigabit Ethernet system. There is a protocol to that. There is a rule for that. Cisco is giving that, like take it and go. So everybody is pouring in their intellectual property into one pool, that pool being RISC-V. Now, so you can make processor for multiple variations. Basically, you can make 32-bit processor for smart TV, low quality application. You can make 64-bit, or let's say you are dealing with security, you can make 128-bit processor with the same architecture. Now it's free for school, and the list is ludicrously huge. Like I spent 15-20 minutes just reading the list. It's like who's who. Like it's huge. The list is huge. Like you will be surprised how many companies are supporting, and even Indian companies are here. So what can we expect in the future? Like everybody is pouring money, everybody is creating this open source. You have to understand, open source has slowly started to change the world, because right now at this point in time, Linux is granddaddy of every operating system, simply because your servers generally are running on Linux system, your Android is a Linux system, your basically satellites also rely on Linux kind of system, and other things along also using Linux, including Google Stadia, that's also using Linux. So Linux is slowly starting to become the mainstream, and right now even Steam is starting to support Linux with gaming support and all that. So Linux is becoming a big thing. That's a free system. That's the benefit of having a quote-unquote open system. And think of it this way: any issue that you have, you can directly figure it out and fix it and share it with others. Benefit of that makes your whole population into what we call basically beta testers. Basically everybody testing is your system, and they can point you out. So it's like you have an issue, you can go to a forum, write it down, and somebody will look into it and somebody will fix it. And you might be like, why would somebody do it for free? Here's the deal. That's how the world works. Like I'm actually surprised that it actually works. Surprising the fact that there are people who are took the Linux kernel as like, yeah, it's good and all, but I wanted to make a network attached storage, so I wrote an operating system based on this kernel, and it's for free. Like they could easily charge it, they can literally charge it, and they can do that because you can take open source hardware and do your own thing on it and then sell it. They can legally do it, but they're like, yeah, just take it and go. That's called free BDS, free NAS right now. So there are people of that caliber. It's like, yeah, I wrote an operating system and gave it for free. Then people are like, okay, I think this operating system is good, but it has an issue with 10 gigabit Ethernet system. Okay, somebody wrote a protocol for that. Some company that is like about to buy a big server, they're like, yeah, the server operating system is gonna cost us like $1 million. What if we use this free DNS? So somebody is like, sir, we can use that, but it will not be very fast. We want 100 gigabyte. The software doesn't support it. Write the code for it. They wrote the code for it. They gave it for free. Now you can literally have a free server operating system that can handle in advanced security, that can handle advanced threat protection, many things. So this happens. Free open source works, and Amazon is a big reason why this is becoming such a big deal. Because think of it this way: there is a 10 people company known as Instagram. How the heck they can handle millions of people in terms of like their IP and all that? They don't. They simply say, Amazon take care of this, and Amazon created an open source architecture. So every engineer that is using Amazon Web Service, they are also taking the ability from the community and they are backfeeding it also. Basically, let's say there is a forum discussion. Hey, I'm trying to handle this many data set. The hex key is starting to break. Somebody is like, I think you can try that, or somebody else is saying, hey, you should try this. If it works, there is a patch. Now it's all for everybody to use. So that's how Amazon is starting to make their bulk of the money, the Amazon Web Services. So even NVIDIA is also opening up their Tensor Core architecture, and they're like, okay, use this architecture to make your AI. Everybody is using it, and it's free, it's open. Like you can make, like there are YouTubers who are using this sort of architecture. So it can become the next big thing. Basically, this architecture RISC-V can become the next big thing. It can be everywhere because it can be like, it's designed for your main replacement of x86. It can easily do that, and it is low power enough that even your Fitbit or things of that nature can utilize it, because there is a 32-bit option, and you can easily utilize that for smartphones and all that. So every Tom, Dick and Harry can use it. On top of that, they can also use it for custom applications like this FADU basically SSD chip. Basically, now you're like, what is that SSD chip? Think of it this way: every hard drive or every SSD you have has a controller chip into it. Now of course, a hard drive controller chip is very easy, that's not expensive. But when you are talking about something that can work at PCI 4.0, that you are talking about 4 gigabytes of read and write, you need a processor to handle that. So this processor is built using that architecture, basically RISC-V architecture. They built it. Now if it works out, so that will translate to this company, which company is investing into this. So basically they will go to Samsung. It's like, hey Samsung, give us your memory chips, and they're like, okay, this is my controller and here's a SSD, which is half the price of, let's say, Samsung's SSD, because Samsung had to rebuild everything from the ground up for their controller. The basically flash memory is the cheap part, the controller is the expensive part. They are having the cheap part, or there are other manufacturers that can also utilize it because it's free. and every time they will have an issue, they will fix it, and everybody else will also get an auto patch. So in this sort of scenario, they are pushing it much further than we can think of. Like, think of it this way: there is this micro semi company that is like trying to take this architecture processor and put a FPGA unit into there, basically field programmable gate array. That's a whole next level of thing. Basically, it's a processor that you can code. So, and it becomes like a dedicated hardware. So the idea with that is like, if they pushed it to upper limit, your motherboard will no longer have a chipset. Basically, you will plug this in, that's it, and you will code it. Of course, they will code it or you will code it. Basically, it will do like, okay, you want how many PCI lanes, this is how your FPGA will be coded, and it will do that. So of course, there will still be limitation. You won't be able to like, okay, let's just put one processor and have 500 PCI cards. That's not gonna work. But you get the idea. Like, chipset will be removed because chipset would be on the processor itself. This sort of thing is not possible with any other architecture. Every architecture is like closed-lipped. You don't even know the driver's code of that, security encryption of that. And here is everything is open. That's why if anybody does any underhanded tactics, it's like, okay, I'm gonna write this malicious code that bypasses the security. Everybody will know it. Like, dude, there is something wrong with this. This is the patch. Fix it. So there is a lot of room for this. Now, will this happen? Will this become the next big thing? I do not know. Nobody knows it. This is the point of future. It could become, it could be just slowly phase out. Nobody knows. So, but I hope that this become, because this is a very good investment in everything. Basically, imagine it this way: the next generation of computer program, if this catches on, they only have to study one architecture and they can be like, hey, I can design a processor for servers. I can design a processor for a smart TV. I can design a processor for your Fitbit or your heart rate monitors. Just studying one. So it can really push humanity to, like, you know, a more optimized and efficient hardwares. I've provided a lot of video down below. You can check it out. Like, you will thoroughly get a bigger idea about this. So this was my presentation on RISC architecture. I hope you liked it, learn from it. In that case, please click the like button. If you didn't like it, don't worry too much about it. You can press dislike. I would urge you to press it twice to show me your extra disappointment. And please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, watch all these other videos.